Welcome back to the Deep Dive. Today we're taking a plunge into a topic that underpins so much of the world around us, from the smallest bookshelf to, well, the grandest bridge.
Hmm.
If you've ever found yourself wondering how engineers make sure structures don't sag, or bend, or even crack under pressure, this deep dive is definitely crafted just for you.
We're exploring the deflection of beams and shafts, essentially, how much they move or deform when a load is applied.
Right.
And it's far more than just a theoretical concept.
Yeah.
Understanding deflection is absolutely critical for a structure's stability, for preventing material failure, and even for figuring out just how robust a design really needs to be.
We've got a fantastic collection of source material today, packed with both rigorous analytical methods and some really clever semi-graphical techniques that make these complex calculations surprisingly approachable.
Yeah, they really do simplify things.
Our mission is to extract the most important insights, give you those aha moments, and hopefully provide you with a real shortcut to being well-informed on this essential aspect of structural engineering.
Wow,
So let's get into it.
let's do it.
So when a beam or shaft actually bends, what's happening to its shape, it forms what engineers call an elastic curve. Imagine the very center line of the beam, and that's the path it takes as it deflects. Right?
That's exactly right. And what's fascinating here is that you can often get a very good mental picture of this curve, even before you do any complex math,
Okay.
just by understanding how the beam is supported. For instance, a support like a pin or maybe a roller,
Right.
that'll prevent the beam from moving up or down at that specific point.
Right. It holds it in place vertically.
Precisely. But a fixed support, like, say, a beam built directly into a solid wall that won't allow any vertical movement or any rotation.
So it's constrained in two ways.
Exactly. And these
Right.
boundary conditions are really your first clues to sketching out what that elastic curve might look like.
And this is where visualization really seems to help, doesn't it?
It does.
If you know the moment diagram for the beam, which essentially maps out the internal bending forces along its length,
Yeah, the M diagram.
you can pretty accurately predict the curve shape.
Mm-hmm.
A positive internal moment will bend the beam concave upwards, kind of like a smile.
Right, like a happy face.
Hmm.
And conversely, a negative moment makes it concave downwards, like a frown.
Okay.
So this brings up an important question. What happens when that internal moment actually changes sign? Goes from positive to negative,
Yeah.
or the other way around?
Yeah. What happened then?
That's where you find an inflection point. It's a critical spot where the curve transitions from, say, frowning to smiling.
Okay.
And right at that point, the bending moment is actually zero.
Interesting.
For you, the listener, grasping these basics gives you a really powerful visual intuition for structural behavior. Our sources even mention a pole vault example,
Oh, yeah.
where estimating the minimum radius of curvature of the pole, they figured it was around 4.5 meters. That helped engineers understand the bending stress in that glass-reinforced plastic pole. It connects the visual shape to the internal stress.
And tying all of this together is a fundamental relationship, isn't there? The moment-curvature relationship.
This is truly a core concept, absolutely key. The curvature of the beam, which is basically just how sharply it bends. Mathematically, it's 1 over the radius of curvature.
1 over rho. Okay.
That curvature is directly proportional to the internal moment, m, applied to it.
Makes sense. More moment, more curve.
Right. But it's inversely proportional to two other really important factors, the material's modulus of elasticity, E, and the beam's moment of inertia.
So the equation is 1 equals MAI.
Exactly. 1 equal MEI. Now, what do E and I really mean in practical terms?
Yeah, let's break that down.
Well, E, the modulus of elasticity, that tells you how stiff the material itself is. Steel has a much higher E than, say, wood or plastic. It resists stretching or compressing more.
Okay, so material stiffness.
Right. And I, the moment of inertia, that isn't about the material. It's all about the shape of the beam's cross-section.
Shape, how so?
And how effectively that shape resists bending. Think about why an I-beam is shaped like an I.
Right, you see them everywhere in construction.
That shape maximizes its I value, its moment of inertia, for the amount of material used. It makes it incredibly resistant to bending, much more than a solid square or rectangle with the same area.
Ah, so it's efficient geometry.
Precisely. This formula, MEI, It isn't just abstract math, it's the fundamental principle guiding engineers. It helps them choose the right materials and the best cross-sectional shapes.
Like deciding between steel and concrete, or choosing an I-beam versus a tube.
Exactly. It explains why a skyscraper's beams might be high-strength steel I-beams to minimize sway, or why a diving board is designed with a specific material and shape to give just the right amount of flexible curve. It's about controlling that EI, the flexural rigidity, to get the performance and safety you need.
Okay, so we've sketched the curve visually, we understand the MEI relationship, but how do we precisely measure that bend and the slope at any specific point along the beam?
Right. How do we quantify it?
Yeah, that's where our first sort of foundational tool comes in, right? Integration.
Exactly. Think of this as the bedrock calculus approach. We start with that moment-curvature relationship, 1 what MEI.
Mhm.
And because deflections in most real structures are actually very small compared to their length.
Which is usually a good thing.
Definitely a good thing.
Oh.
We can simplify the math a bit, and the relationship becomes a second-order differential equation. EI dv dx x says m, where v is the vertical deflection.
Okay, EI times the second derivative of deflection equals the moment.
Correct. Now, integrate this equation once with respect to x, and you get an equation for the slope of the elastic curve.
The angle of the curve at any point.
Yep. Integrate it a second time, and you get the displacement v itself, the exact mathematical shape of that elastic curve we were sketching earlier.
So just integrate twice, and you're done. Sounds almost too easy.
Well, not quite. Each time you integrate mathematically, you introduce a constant of integration, a C1 and a C2.
Ah, the constants. I remember those from calculus.
Right. And these aren't just arbitrary numbers. They're determined by your specific boundary conditions.
The supports we talked about earlier.
Exactly. For example, at a fixed support, we know the beam can't move down, so the displacement v is 0 there. And it can't rotate, so the slope, dv dx, is also 0 there.
Okay.
At a simple pin or roller support, we only know the displacement v is 0. The beam can rotate there.
I see.
These known conditions at the boundaries give you the equations you need to solve for those constants, C1 and C2, for your specific beam.
Okay, that makes sense for simple cases. But what if you have a beam with, say, a heavy weight dropped right in the middle, a concentrated force, or maybe a distributed load, like a pile of bricks, that suddenly stops partway along the beam?
Good question. That complicates the moment function.
Because the moment equation would change at the point of the load, right?
Absolutely. That's where continuity conditions become essential. If your loading is discontinuous, meaning it changes abruptly like that, you typically have to write separate moment functions, M1, M2, etc., for each segment of the beam between the discontinuities.
So multiple integrations, multiple sets of constants.
Potentially, yes. And then, crucially, at the points where these segments meet, the slope and the deflection must be continuous.
Meaning they have to match up perfectly from both sides.
Exactly. The calculated slope from the left segment's equation must equal the slope from the right segment's equation at that joining point. Same for the deflection. This ensures the elastic curve is physically smooth and unbroken, no kinks or jumps.
Okay.
It makes the math a bit longer, but it's an incredibly versatile method. It works for pretty much any loading scenario you can throw at it. Our sources show this in example 12.3, determining the maximum deflection of a simply supported beam with a concentrated force. It requires setting up 2 coordinates and using those continuity conditions.
All those separate functions and continuity conditions for discontinuous loads, though. It sounds like it could get pretty tedious, a lot of bookkeeping.
It certainly can be. There's definitely room for error with all those constants and matching conditions.
Is there a way to streamline that, a kind of shortcut to get to a single, elegant solution, even with those messy loads?
Absolutely. This is precisely where discontinuity functions truly shine. They are a really clever mathematical tool.
Okay, I'm intrigued. Discontinuity functions.
Yeah. Imagine you have a beam with several different loads starting and stopping at various points. Instead of writing multiple M equations, discontinuity functions let us write a single expression for the loading, or more usefully for the internal moment M that's valid across the entire length of the beam.
A single equation for the whole beam, even with jumps in the load.
Exactly. They use a special notation, often called Macaulay brackets. They look like angle brackets. These brackets define terms that effectively act like mathematical switches. Yeah, a term like xn is defined as 0 until x actually reaches the value a, the point where the load starts. Then, for x greater than a, it behaves just like a normal xan.
So it turns on the effect of the load only after you pass its starting point.
Precisely. For instance, a distributed load starting at XA, like the triangular loading mentioned in example 12.5, would be represented by a Macaulay function that's 0 before A and then represents the load after A.
Okay.
And there are related functions, sometimes called singularity functions, designed specifically to handle concentrated forces and couple moments, which are even more abrupt. They essentially activate only at a single specific point.
So it's a way of making these physically abrupt real-world problems, like you mentioned bridge decks with different vehicle loads, or beams maybe supporting multiple unevenly placed bags of cement.
Right, those complex scenarios.
It makes them mathematically continuous and clean within a single equation.
That's the beauty of it. It eliminates the need for writing separate segment equations and worrying about all those continuity conditions. You just integrate the single moment expression twice, and you only have the two initial constants of integration, C1 and C2, to solve using your overall boundary conditions. It's much more elegant and less error-prone.
That sounds incredibly powerful, a real game changer for complex loading.
It really is a very efficient technique.
Okay, let's shift gears a little bit. We've talked about the integration method, both the direct way and the streamlined version with discontinuity functions. What if you're someone who prefers a more visual approach, maybe something less reliant on pure calculus to understand how a beam deflects?
Then the moment area method is definitely something you'd want to look at.
Moment area method.
It's often called a semi-graphical technique. It's really elegant because it directly connects the geometry of the MEI diagram, remember that's the internal moment, divided by the beam's flexural rigidity, EI.
The M over EI diagram.
It connects the area and moments of area of that diagram directly to the slope and displacement of the actual elastic curve.
So geometry tells you about deflection.
In a way, yes. It's particularly convenient when your MEI diagram happens to be made up of simple shapes like rectangles, triangles, maybe parabolas, where you can easily calculate areas and centroids.
Okay, so how does this visual method work? Are there specific rules or principles?
There are two key theorems. They're quite elegant. Theorem 1 is about the change in slope.
Okay.
It states that the angle or the change in slope between the tangents drawn at any 2 points on the elastic curve. So imagine drawing tangent lines to the bent beam.
Right.
That change in angle between those two tangents is equal to the total area under the MEI diagram between those same 2 points.
Just the area, that's it.
Just the area under the MEI curve between points A and B gives you the change in slope between A and B. And the sign matters. A positive area corresponds to a counterclockwise change in angle.
Wow, so I can just calculate an area, maybe from a simple shape on the diagram, and that tells me how much the beam has rotated between 2 points. That's wonderfully intuitive.
It really is. It gives you a great feel for how the bending moment accumulates to create rotation.
Okay, so that's theorem 1 for slope. What's the other one?
Theorem 2 relates to displacement, specifically the vertical distance between tangents.
Vertical distance.
Yes. It tells us that the vertical distance measured at one point, say point B, between the tangent line drawn at another point, say point A, and the actual elastic curve at B, or more precisely, the tangent extended from A.
Okay. Bit more complex to visualize.
It is slightly, but think of it as the vertical deviation of a point from the tangent drawn at another point. That vertical distance is equal to the moment of the area under the MEI diagram between those 2 points, A and B.
The moment of the area, like finding a centroid.
Exactly. You calculate the moment of that MEI area, but you take the moment about the point where you want to find the deviation, so about point B in our example.
I see. So area gives slope change, moment of area gives tangential deviation, which relates to displacement.
You've got it. It means you can quickly find things like, for instance, the maximum displacement at the free end of a cantilever beam, which is often just the tangential deviation from the fixed end. Example 12.8 in our sources shows exactly that.
Right.
Or you could find the slope at a specific point on a symmetrically loaded shaft, like in example 12.9, sometimes more easily than setting up the full integration.
It really does offer a different perspective, doesn't it? A more geometric intuition compared to the integration method, especially useful maybe when the MEI diagram is nice and simple.
Precisely. It's another powerful tool in the engineer's toolkit.
Now, thinking about the real world, many structures aren't subjected to just one simple load, are they? I mean, a bridge has traffic, its own weight, maybe wind.
Absolutely. Real-world scenarios are almost always combinations of different load types acting simultaneously. Multiple forces, distributed loads, maybe even moments from connections, all acting at once.
So how do engineers tackle that kind of inherent complexity? Does everything just get thrown into one giant integration problem?
You could do that, perhaps using discontinuity functions, but often there's a much more practical approach. That's the perfect scenario for the method of superposition.
Superposition. Okay, sounds important.
It is incredibly useful because the relationship between the applied load and the resulting deflection is linear, assuming we're dealing with small deflections, which is usually the case in structural design.
Which means doubling the load doubles the deflection.
Exactly. Because of that linearity, you can essentially break down a complex loading situation into several simpler individual loading cases.
So you take the bridge with traffic and weight and wind.
And you analyze it as case 1, just the weight. Case 2, just a typical traffic load pattern. Case 3, just the wind load. You calculate the deflection or the slope or stress, whatever you need for each individual load, as if it were the only one present.
Okay, find the deflection for each simple case. Then what?
Then you just algebraically add up all those individual results, the deflections from case 1, case 2, case 3, to get the total deflection under the combined complex loading.
So instead of one giant, potentially very messy problem, you solve several smaller, usually much easier ones, and then just sum the answers.
That's exactly it. Add them up. It sounds almost too simple, but because of linearity, it works perfectly.
That sounds incredibly efficient, especially for managing what could otherwise be overwhelming information.
It truly is. And what makes it even more powerful in practice is that engineers frequently have access to extensive tables.
Tables of what?
Tables of pre-calculated deflection formulas for dozens of common standard loading cases, like a simply supported beam with a point load in the middle, or a cantilever with a uniform load. These are often found in appendices of engineering textbooks and handbooks, like Appendix C mentioned in our sources.
Ah, so you don't even have to do the integration or moment area yourself for those standard cases.
Often, no. For many practical design problems involving combinations of standard loads, you're literally just looking up the formulas for the deflection caused by each component load and adding the results together.
This really feels like a genuine shortcut to being well-informed and getting practical answers quickly. I'm thinking about example 12.13, where a simply supported beam had both a distributed load and a concentrated force. Using superposition, you just find the deflection from each one separately, using standard formulas perhaps, and add them up.
Exactly that. Or think about example 12.16, which was a beam supported by springs.
Oh, right.
There, you'd combine the deflection due to the beam bending itself with the rigid body displacement caused by the springs compressing. Superposition lets you handle these combined effects systematically. It shows how you can break down seemingly complex systems into manageable parts.
Okay, we've talked about all these powerful ways to find deflection integration, discontinuity functions, moment area, superposition. They all seem geared towards figuring out how much a beam bends, given the loads and supports. But what happens when a beam has, like, too many supports?
Too many supports.
Yeah, what if there are so many supports that you can't even figure out the support reactions, the forces the supports push back, with using just the basic equilibrium equations we usually start with? Like sum of forces equals 0, sum of moments equals 0.
Ah, right. That's a very important situation. That's when we say a beam is statically indeterminate.
Statically indeterminate.
Yes, it means the number of unknown reactions forces or moments at the supports exceeds the number of available independent equilibrium equations from statics.
So math-wise, you have more unknowns than equations. You can't solve it directly with just statics.
Precisely. Those extra supports, the ones beyond what's strictly necessary to just hold the beam up without it falling down, are often called redundants.
Redundant. So
And figuring out the forces or moments associated with these redundant supports is the crucial first step before you can analyze stresses or deflections properly. Think back to that bridge deck we mentioned right at the very beginning.
yeah.
It's vital to carefully monitor its deflection. And structures like that, continuous beams over multiple supports, are very often designed to be statically indeterminate. It often adds extra safety and stiffness.
Okay, so if you can't use equilibrium alone to find those redundant reaction forces, how do you find them? How do you bridge that gap?
This is precisely where the deflection methods we've just spent all this time discussing become absolutely indispensable. They provide the extra equations we need.
Ah, so calculating deflection helps you find the unknown forces.
Exactly. You effectively use what's sometimes called the force method or the method of consistent deformations, which cleverly employs the principle of superposition again.
Superposition again.
Okay, here's the idea. You choose one or more of those redundant reactions, say, an extra roller support in the middle of a beam. You temporarily remove it, or rather, you remove the constraint it provides.
So you pretend that middle roller isn't there for a moment?
Yes, conceptually. This makes the beam statically determinate, maybe just a simple beam supported at the ends. We call this the primary beam.
Okay, so now it's solvable by statics, but it's not the original beam anymore.
Correct. So first, you calculate the deflection of this primary beam at the location of the removed roller, just due to the original external loads. Let's say it deflects downwards by some amount.
Makes sense.
Then, as a separate load case, you apply the unknown redundant force, the upward force from the roller we removed, let's call it R, back onto the primary beam at that same point. You calculate the upward deflection caused by just this unknown force, R. This deflection will obviously be proportional to R.
Okay, so deflection due to loads and deflection due to the unknown reaction are.
Right. And now comes the key part, the compatibility equation.
Compatibility, meaning things have to fit together.
Precisely. You write an equation that describes the physical reality, the geometric compatibility, at the location of the redundant support we removed. In our example, we know that in the original indeterminate beam, the actual deflection at that middle roller support was 0. It couldn't move down because the roller was there.
Right. The roller prevents displacement.
So the downward deflection caused by the external loads on the primary beam, plus the upward deflection caused by the unknown redundant force R on the primary beam, must sum up to
0.
Exactly. That gives you an equation where the only unknown is the redundant force R. You solve that equation for R.
And suddenly you know the reaction force at that extra support.
You do. And once you know all the reaction forces, the beam is effectively determinate, and you can proceed to find moments, stresses, and detailed deflections anywhere along its length using the methods we already discussed.
That makes so much sense. It's like using the beam's own deflection behavior to figure out the forces holding it up. I remember seeing example 12.21, where a beam was supported by a vertical rod.
That's a classic indeterminate problem.
The force in that rod was the redundant. And solving for it required considering both the beam's deflection downwards and the rod's own stretch upwards, making sure the final position was consistent.
Exactly. It's a beautiful example of how these deflection analysis tools are not just for checking final designs, but are fundamental to solving these more complex but very common indeterminate structures. It's a testament to how these seemingly complex methods ultimately lead to really elegant and practical solutions for very real engineering challenges.
Wow. Okay, that was a truly deep dive into the fascinating and clearly critical world of beam and shaft deflection.
We covered a lot of ground.
We really did. We journeyed from just understanding how a beam visually bends and the idea of the elastic curve through the detailed math of integration.
The differential equation.
The clever shortcuts of discontinuity functions, the visual power of the moment area method,
Connecting geometry and bending,
the simplifying genius of superposition for handling complex loads,
breaking it down.
and finally, seeing how all these tools come together to solve the ultimate puzzle of statically indeterminate structures. It's quite a toolkit.
It really is. And what we've uncovered today, I think, is not just about the formulas and the theorems. It's really about the fundamental principles that ensure the safety, the stability, and the integrity of practically everything built around us.
Yeah, from the chair you might be sitting on right now to the tallest skyscrapers outside your window.
Absolutely. It's everywhere.
Exactly. And, that brings us to a final thought for you, our listener, to perhaps mull over. We've spent this time exploring how engineers calculate deflections, how they use these tools to ensure structures are sound and safe.
The design and analysis part.
Right. But thinking beyond the calculations, what might be the unseen costs or the hidden implications when these fundamental principles of deflection and stiffness are overlooked, even just slightly, in the design or maybe the construction of the very structures we rely on every single day?
That's a profound question, isn't it? It really prompts us to consider the quiet yet absolutely immense importance of getting these engineering fundamentals right, not just on paper, but in the real built environment that surrounds us and, frankly, safeguards our daily lives.
Something to think about. Thanks so much for joining us on this deep dive. We hope you feel a little more well-informed and maybe a little more curious about the forces both seen and unseen that are shaping your world.